Good morning, guys. My name is Huyen Tuet Dao, and I'm here to talk to you guys about green threading in Flex. What is green threading? I will explain it in just a little bit, but basically what we're here to talk about is, as developers, and as the Flash platform has been growing, we as developers are asked to create more complex applications, and along with that goes creating applications that are more computation intensive, that are more data intensive, and along with that goes these situations sometimes we find ourselves and our applications experiencing, slowdowns, choppiness, hangups, and at the worst, freezing and crashing. So I just want to talk to you guys about, why does this occur? And what is it about the Flash platform and the Flash player that brings this situation up, and what we can do about it? And in particular, what green threading can do about it. So just real quick about me. I know I said my name real fast. If you want to try to pronounce it, it's something like Huyen Tuet Dao, but it's okay, whatever works, just to give it a shot. I don't mind either way. I've been a Flex developer since about 2006 with Flex 2. This is my third time speaking, and I'm really glad to be here with you guys. And the only other thing I really do other than develop is play video games. So if you're a Mass Effect 2 fan, that's for you guys. So what are we going to talk about today? So we're going to talk about this problem, with computation-heavy applications and slowdowns, freezing, crashing. We're going to talk about some solutions. We're going to talk about green threading and how that solves our problem. We're going to compare all these solutions. I'm going to give credit where credit is due, because there's been a lot of really great work done by a lot of really intelligent people on this subject, so I want to give them props. We'll wrap things up, and hopefully we'll have time for questions at the end. Okay, so the problem. So the Flash player is really well suited to doing certain things, and that's not the problem. But it was really well known for doing great animation. When you're creating your Flex applications, you can have tons of components, handling user input, firing off this event, doing that, effects, graphics, everything. It seems that the Flash player gives you a level of concurrency, doing several things at once. However, what can happen is sometimes one of those components can get hung up. If it's doing a lot of processing, what can happen is the Flash player hangs, freezes, and crashes. And it doesn't even take complex code for this to happen. You could just be doing some really simple arithmetic operations, but if you're doing a lot of it, if you're requiring a lot of processing time, your code can hang up. And I'm just going to show you a little example of what I mean. Okay, so I'm just going to do some data parsing here. And the data I'm looking at is pretty simple. It's not very interesting or sexy or anything. It's pretty old data. It's basically a log of visits to the MSNBC website on some date in 1999. So each line of the data has just a series of integers, and the integers represent some category in MSNBC. Front page, sports, world news, and each line is basically what category and what a page on a certain category that the visitor went to. So the first visitor maybe took a look at 2 pages on the front page. Second visitor maybe was checking their favorite team, so they just took a look at one page on the sports category, and that's all that is. And there are about 990,000 lines of this data. Pretty simple. Okay, so what I'm going to do with this data is I'm just going to parse through it, and I'm going to create some data objects. Let's see. Okay, so I have a really simple. Okay, so I have a really simple class here that's just a data object, and all it does is freeze. Okay, so all it does is just kind of looks through each line, and as it's being parsed, it just kind of increments, a visit for every category as appropriate. And so I have my data object, and I have this kind of parser class that takes care of, parsing through this line of data. So anybody wanting to use my parser just calls this public method parse, passes it an array of strings, which is, consisting of the data that I just showed you guys. It just basically sets up, a loop to, loop through all the lines of data, creates my data objects here, sticks them in an array collection, and in my actual application, which I'm going to run for you guys. Okay, so that's basically what my application is doing. It's calling this parser. It's going to parse this, 990,000 lines of data. Okay. All right, so here's my application. It's pretty simple. So what I'm going to do is I'm loading in that text data. I've got a data grid that I'm going to populate once I'm finished parsing my data. I've got a progress bar to kind of see where I'm at. And what we're talking about here is basically, responsiveness, freezing. How can we keep the application, responsive and, So to test that, I've got this little click me button. And basically every time you click it, changes styles, changes sizes, has a little bit of animation effect, just so we can see, how our responsive our application is staying while we're parsing this data. And I'm just going to go ahead and start parsing it. Oops. And yeah, as you can immediately see, it has frozen. It's not responding to any of my mouse clicks. It's not, the progress bar isn't moving. It's basically stuck. So, and this is exactly what we're talking about here. What I'm doing is not really complicated. I'm just parsing some text data. I'm just sticking it in an array collection. But the fact is that I am parsing 990,000 lines of data, and the Flash player is so busy doing that for me that it has no time to do anything else and no time to respond to me. And I'm sure that's going to crash while I go back to my slides. Okay. But let's press on. So, okay, so the problem. So the problem basically revolves around the Flash platform's event-driven frame-based architecture. I'm sure you guys are familiar with Swifts, and basically they're movies, right? You've got a bunch of content divided up into frames, and the frames are played more or less according to a timeline. So like I'm showing this diagram here, you've got your little timeline, a bunch of number of frames. There's content on each one, and more or less, they get played through sequentially. Your Flex application is no different. It just has a very particular form to the timeline. In a Flex Swift, there's 2 frames. The first frame has just a bunch of bootstrapping, preloaded code, gets your application set up. All of your application code that you actually write is in frame 2. So when your Flex application is actually running, it's just going into frame 2 over and over again, running your application code. Oh, okay, so like I said before, the Flash platform is event-driven. Just about everything is triggered by an event. And when the events get triggered, they get pushed onto event queue, and the Flash player handles them one at a time. To get to the next frame, an event is triggered. So here I have my event queue, and it's got events from a bunch of different places. You got some events that were dispatched by content of some sort in frame 1. You have some user input via the keyboard and the mouse. And you have, at some point, the all-important frame event. Okay, so your Swifts play at a certain frame rate, a number of frames per second. So that means that each frame has to play in a certain amount of time, which is 1 over the FPS. So your Flash player, the default frame rate is 24 frames per second. So in order for it to keep up with this frame rate, it has to execute each frame in about 42 milliseconds. An important thing to note is that the frames per second, the frame rate that you tell Flash player to play at is actually a minimum. It's not a minimum, sorry, it's a maximum. Basically, your Swift can run no faster than what you set the FPS to be. So what happens is if you've got some code running in this frame and it's taking longer than the allotted time, than whatever this 1 over FPS is, the Flash player is so busy processing whatever event that spawned this code that it can't get to the next frame event on time. And then so you get an application that slows down, you get an application that freezes, and in worst cases crashes. So non-responsive window in Windows, and that lovely beach ball of death in Mac. So another way to look at it is thinking of Ted Patrick's elastic mental racetrack. And it's this really cool model that, in which he kind of explains when certain kinds of code gets executed in like a single frame. So in a frame of your Swift, you've got code execution happening in the first half of the frame, and then rendering happening in the second half of the frame. Now, this racetrack, this time that the frame takes up, is going to stretch out and accommodate whatever code it is asked to execute. So basically, whenever the Flash player is told do this in a frame, it'll do every single thing that you ask it to do. And if it needs to take more time, it will. And unfortunately, there's no built-in way for the Flash player for you to defer, or the Flash player to defer like certain bits of code for execution later, It's just going to execute everything. So what happens is if the Flash player starts executing some code and it starts running along, then you can see that, that code execution side of the Elastic Racetrack is just going to keep stretching out. And the longer that it actually keeps processing, the longer and longer that racetrack is going to stretch out. And basically what happens is if you have some really long running code, the Flash player basically gets stuck on that first half of the track. Okay, so that's the problem. So how do we solve it? So we've got some kind of code block, some algorithm, some kind of process that's taking a long time to run. So what we want to do is just break it up into smaller jobs, smaller batches. And since the problem is that we're trying to do all this work in one frame, to fix that, we want to just make sure that we break it up into these smaller batches and make sure that we trigger these batches at different times, different frames. That way we give the Flash player a chance to catch up on the event queue. It can process other events, user input, and those all-important screen updating events. So there are a few different ways you can break up this process. One way is you can use the call later function. Call later is a public method on the UI component class. It's basically a method that you can pass a function. And basically what it's going to do is that every function that gets passed to call later gets put on a queue. And at some point, generally at the handler for the render event in a frame, it's going to try to go ahead and process all those functions that you queued up for it. Sometimes that doesn't quite work out. Sometimes there might be some invalidation problems, and so the queue will get moved to kind of being handled on the interframe event of the next frame. Another important thing to note is that in the documentation for this method, it states that some features like effects can cause queued functions to be delayed until the feature completes. So basically, whenever you pass a method to call later, it's a little bit fuzzy about when exactly it's going to execute. It'll execute later, but depending on what else is going on in your application, it could be sooner or later. Another thing to note is that when you actually call later on the UI component method, or the UI component, some UI component instance, it has to be an instance that's displayed on the stage. And that makes sense, right? If we're kind of handling this queue of functions during the render event, the component has to be rendered. So, because of all this, I'm not a big fan of doing this, and I'm not going to talk about it much further. But if you find it suits you and it's there, you can certainly do that. So the two that I'm going to go into detail about is number one, using the enter frame event. So we were talking about scheduling batches of work, at different frames. So the simplest way to do that is to say, all right, I'm just going to do a bunch of work at the beginning of a frame. So I'm just going to listen for this enter frame event and then just fire off a batch of work to do. Second way of doing it is to use timer objects. So you have these timer objects, in the framework, and basically they're clocks, of course, and they tick. And they tick off every, so many milliseconds. So what you can do is set up a timer, listen for these ticks, and then just fire off a batch of work every time the timer ticks. All right, so let's take a look at a little code. So here's a little bit of code that can show you how to use the call later method to schedule some batches of work. You've got some UI components somewhere that's being displayed. You've got some variables that are kind of bookkeeping, progress keeping variables. In my example, I have a for loop, so I'm just going to call them iterations. So I've got a variable to track how many iterations I've done, how many iterations I need to do, and then I've got this function here, which is run loop, and it runs a loop. It runs an iteration of my loop. And so when you're using this method, or this technique rather, you're just going to create this function. You're going to do some unit of work in this function. You're going to increment your bookkeeping progress variables, and then you're going to check your stopping condition. And basically, if you haven't finished doing all the work you need to do, just use call later on whatever object you want to call it on, and then pass it your method for doing work. And here it's going to be run loop. And then basically, whenever it's able to, the object is going to go ahead and process that queue with run loop on it. So another way I talked about is using the enter frame event. And the process is pretty similar, a little bit different. So just like before, I have some progress variables, how many iterations I've done, the total number of iterations that I need to do. But in this case, what I'm going to do is I'm going to add an event listener to the application, the application object. and I'm going to have it listen for enter frame. And then my event handler for enter frame is going to be, this run loop, method. And just like before, I'm going to do some unit of work. I'm going to increment my progress variables. I'm going to check my stopping condition. If I have finished doing all the work that I need to do, I'm just going to go ahead and remove that event listener so we don't run any more work the next frame. Okay. Oh, another thing to note, if you're thinking about this for Flex 4, is that application.application is deprecated. You'd use instead flexglobals.topApplication. So just it's flexglobals.topApplication. And so that's Flex 4. Okay, so let's take a look at an example of this. Ooh, and here's my crashed application. Okay, so I have a new parser here, and here's my enter frame parser. Okay, so just like before, I've got my parser class, and it's got some public method that somebody using this parser just passes an array of data. And here I've got my bookkeeping variables, number of lines parsed, number of lines total to parse, and I set up my array collection to catch all my data objects. And here I'm adding my enter frame event listener to the application object. And here in the actual event handler itself, I'm going to take that line of data, I'm going to parse it, create my data object, throw it on the array collection. I'm going to increment my progress variables, and I'm going to check my stopping condition. If I'm done, I'm going to just go ahead and just take that event listener off. And I'm also going to dispatch a complete event. That's just for my application, just to let everybody else know, hey, we're done. And if not, I'm going to dispatch a progress event, just let them know, hey, we're still going here. So I'm going to open up my application here and run it. Okay, so just about the same, application as before. Got my data grid, got my progress bar, got my click me button to make sure that everything is still responsive and running. So I'm going to go ahead and parse the data. All right, great. So we can actually see that this progress label is updating. The progress bar is moving. It's just very, 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 very slow. And the most important part is my click me button is registering my clicks, animating, resizing, restyling. Awesome. Okay, so I'm just going to stop that. Okay, so that was enter frame. Now, what we can also do is use a timer. And again, pretty similar process. You start off with some bookkeeping variables to track where you are, how much you need to do. And in this case, we're going to just go ahead and just start up, start an instance of a timer object. And we're going to give it some kind of, amount of time between ticks of this clock. We're going to add an event listener to listen to these ticks. And when we actually, find one, we're going to go ahead and do run loop. Just like before, we're going to do, the work of one iteration here, update our progress variables, and then check our stopping conditions. This time, if we find that, we finished doing our work, we're just going to stop the timer. Otherwise, we don't have to do anything else. And then the next time the timer ticks, it'll do run loop again and keep doing the work that we need it to do. Okay, so come back to my code here. And I'm going to pull up my parser that uses timer. Now, as you kind of noticed before, my other example, enter frame, was running really slowly. You couldn't even see the progress bar moving. So if you think about what I was doing one iteration of my loop per frame. So a frame, like I said, if we go default, is about 42 milliseconds. I had 990,000 lines of data. So in order for me to finish parsing that, it would take about 11 hours. So, the good thing was that our application was responsive. The bad thing is that your user is going to have to sit there for 11 hours to see all this boring data parse. So how can we fix that? Well, obviously, we weren't doing enough work. We were spreading out our work way too far. So to fix this, let's just do more work every time we actually do work. So in this version of the parser, I'm adding a little property here, num iterations per. So every time I actually do work, I'm going to do this some number of iterations of my loop instead. So just like before, my parser's got this public method that people call to use it, pass it some data. I'm going to set up my bookkeeping variable, set up my array collection for my data objects. And here I'm instantiating a timer object. I'm going to set the time to be about a frame rate just to kind of keep things kind of similar to my other examples. I'm going to add an event listener for that timer event, for that ticking of that clock. And then my event listener is parseLine. And just like before, I take some string. I'm going to parse this visitor view data object out of it. I'm going to stick it in my array collection, and I'm going to update all my bookkeeping variables. And in this case, I'm doing a certain number of iterations every time I do work. So I'm going to do a multiple number of these, whatever num iterations per was set to. After I'm done all that, I'm going to check my stopping condition. Have I finished doing all my work? If I have, I'm going to stop the timer. And just to be neat, I'm going to take that event listener off the timer, dispatch my complete event, let everybody else know I'm done. If I haven't finished, I'll just dispatch a progress event and let everybody know, hey, we're still going here. Okay, so got my timer application, and go ahead and launch it. And surprise, surprise, pretty much the same as before. Instead, this time I've got a little numeric stepper that will allow me to control how many iterations I'm going to do every time this timer ticks. But I've got my data grid, I've got my progress bar, and I've got my little click me button. Okay, so let's go ahead and start this, and just, again, if we do one iteration of work every time this goes off, it's really slow, progress bar isn't moving, I'd have to sit here for 11 hours, and it wouldn't be fun. So let's stop that, and let's try something different. Let's try doing 2,000 iterations every time the timer ticks. Set that and parse the data. And cool, we can see that it's going a little bit faster. Progress bar is actually moving, that we can see. We're already at about 10%, whereas before we might have been like 1/10 of 1%. And the best part is, click me button still works. Okay, well, okay, we did 2,000. Can we do a little more work? Maybe speed things up a little more. We'll reset that. Let's try 5,000 and parse the data. Okay, so we can see the progress bar is moving a little bit faster. It's not as smooth as it was before. And we can see that at the same time, the click me button's working, but it's kind of laggy, it's a teeny bit choppy, not as great in terms of responsiveness as we did, we did a little bit less. So let's just have a little fun. Let's try 20,000, let's see what happens. Okay, I'm going to parse my data. And as you can see, it's parsing data pretty quickly, but now you can't even see, that effect that I put on the resizing and the styling. So, it's kind of like in our kind of effort to make things more efficient, we've looped back around to the same problem. We're doing too much work in a frame. The Flash player isn't able to keep up with all the events that it has to handle. So things get choppy, things slow down. Okay, so just to recap, the couple solutions that we took a look at, that we've taken a look at, the good part, when we did it right, the event queue could, process other events between batches of our work, application remain responsive. Awesome. The not so good. Okay, number one, the code becomes a little more complex. Before I just had a really straightforward for loop, it was just grinding through the data, and getting all that done. Now I've got event listeners, I got to do a little bit of management, okay, a little bit more complexity. Another not so good thing is it can take much longer to finish the job for two reasons. Number one, you're literally spreading out the work that you do over time. So instead of doing all that work in, I think it would have finished, if it had finished in about 60 seconds, it would take 11 hours in the worst case. Not good. Another reason it might take a little bit longer is that you do have a little bit more overhead. And another thing that's kind of good but really not so good is that we find ourselves in a situation where, depending on how we use these techniques, we kind of have to fine-tune the amount of work we do, and sometimes maybe play with how often we do it. And this can be time-consuming. It didn't take that long for me to do it right now, but again, it's still a lot of trial and error, figuring out where your sweet spot is. And then not only that, but say your application changes. Maybe the data that you're processing changes format. Maybe the amount of data that you have to do changes, or maybe you start kind of adding things to your application that require a lot of processing too. Or you're gonna have to go back in and refine this, retune this, just to get it back to that optimal place between amount of work you do and amount of time you do it in. Okay, so that leads me to green threading. And green threading kind of springs from the idea of multi-threading. Now, strictly speaking, developers can't, at this point, can't use multi-threading on Flash Player. That isn't to say Flash Player doesn't multi-thread. It does have some multi-threading that it uses for networking, sockets, It has some watchers that watch your code for the timeout, just like my application before timed out. There's a watcher kind of sitting parallel to it, making sure that it's still running. But you as a developer cannot access those. Now there is true threading, and that's available via Pixelbender. And Pixelbender was designed for media processing. Admittedly, I haven't done much with it, but it's kind of a cool way of taking advantage of the fact that on the Flash platform, you can run shaders, filters, and blenders in true multi-threaded fashion. So what you can do is if you want to go this route, you can take your problem space and find some metaphor for it in shaders, filters, and blenders, and you can convert your problem space to Pixelbender's problem space that way. And if you find that works for you, if you find that fits your problem, then cool, go ahead and use it, and you'll be able to multi-thread things. But what if it's the case that we can't, either for some reason we don't have access to Pixelbender, or we can't find a really good kind of model for our problem? Well, we use green threading. So what's a green thread? Well, before, our problem is that we have a bunch of code that we want to execute, and it kind of executed all at once, it slowed things down. We want to give ourselves a little more control over when code gets executed, which is what we try to do with the timer and the enter frame. So what we can do, though, is take this idea of multi-threading and emulate threads in our developer code. And these emulated threads are the green threads. And it's kind of a similar idea to how other platforms provide threading when you're still on a single processor system. It's this idea that you have, a bunch of things going on at the same time, a bunch of threads. And if you're on a single processor and you want to make things look like they're multi-threaded, you basically just have to give everybody a turn and give them a turn kind of quickly. You get a turn, you get a turn, you get a turn, you get a turn, and you swap off and you give people time fast enough that it looks like you're multi-threading, that you have some concurrency there. So before, with enter frame and timer, we had this idea of, I want to schedule some work at different times and give the Flash player a break in between. With green threading, the idea is a little bit different. We're looking at things from a different perspective. Instead of thinking, how much is the best amount of work to do every time I do work, I'll be like, all right, this piece of my code is important, so I want to do as much work as possible on it every single frame. But I want to make sure that the Flash player has time, to catch up, that it can process other events, that it can render any screen updates. So I'm going to just leave some time so that the Flash player can do this. So how are we going to kind of make this into a concrete technique? All right, so we want to leave some specific amount of time left for all the other events to process. Call it epsilon. So we're going to take our long-running code, our algorithm, our process, whatever you want to call it, and we're going to break it up into basic blocks, just the smallest amount of work you could conceivably do at one time. And then what we're going to do is have our green thread run that basic block. And every time it runs that basic block, we're going to check how much time we've used so far in the frame. And we're just going to keep checking. And every time we are about to do some work and we check the total time that we used, if it's more than the total time in the frame, minus that epsilon we're leaving for everybody else, the green thread is just going to stop. Just let everybody else do their thing, and then just wait around for the next frame to start up again. Okay, and kind of like a little graphical kind of view of how this works. So I might have some other code that executes in the frame before the green thread actually starts. My green thread is going to run one block, and it sees that, wow, I have plenty of time left. I'll run another iteration. It checks the time, sees it has plenty of time left. It's going to run again. And then it's going to just repeat that process and over until it gets to a point where it says, all right, if I run one more iteration, I'm going to start intruding on that epsilon territory. So we're going to stop, let everybody else in the frame that's scheduled for this frame do whatever they want to do, and we'll just wait for the next frame to come up and start again. All right, so going back to my code. All right, so I have my green thread parser. Oh, wait, actually, oops. All right, sorry, I skipped over a bit there. All right, so all this functionality has already been encapsulated in this class. And this class is called Green Thread. It was written by a developer named Charlie Hubbard. It's available up on Google Code at this address. And basically all this functionality, all this management, all this time checking, Charlie's kind of built into his green thread and a couple other managers that are in this library. And he also provides some really cool things like statistics, you know, seeing how long things take to run. He's got progress monitoring via events, kind of like I was doing earlier with firing off events so that you can notify the rest of the application about where your green thread's at. And using it is really simple. You just take your code block, your algorithm, your job, and just turn it into a green thread. Well, how do we do that? So we're just going to take Charlie's green thread class and subclass it. And here's, you know, my little subclass, my green thread algorithm. And to use it, you really only have to do two things. You're going to override two methods. One of them is the initialize method, and it's just like what it sounds like. It just basically sets up your green thread to run. I've got some bookkeeping variables like I had before. In Charlie's class, they're called progress and maximum. And it's kind of mirroring that progress bar. The progress bar component has these two variables on it, so I think it's, you know, it kind of goes along with there. So I'm going to initialize my variables, and the second thing I need to do is override this run method. So the run method is where all the meat of your work is getting done. All that work of your iteration is going to happen in run. You're going to update your progress variables however you need to. And the easy thing is that you just check your stopping condition. If you're done, return true. If you're not, return false. And then the green thread and all those management classes take care of the rest for you. All right, so now we're going to look at some actual code. So here's another parser class that I wrote. It has that same public method parse that someone using it can just pass in an array of data. And as you can see, it extends Charlie's green thread class. So here's my, you know, parse function that people outside, you know, wanting to use it call. And it'll run start. And when start happens, it's first going to call my initialize, you know, my overridden initialize function. And here in mine, I've just gone ahead and, you know, initialize the progress and maximum to whatever, you know, is appropriate for me. I've, you know, set up my array collection to catch all my data objects. And down here, I have my override of run. And run is doing the same amount of work, the same work that we were doing before. Just taking that, you know, that line of data, parsing out a data object of it, you know, adding it to my array collection, updating my progress variables, and then checking my stopping condition. If I'm done, return, I think I mixed that up. If you're done, return false. If you're not done, return true. And I should change that. So if you need to keep going, return true. If you're done, return false. Sorry about that. Okay. So seeing it in action. All right. So I've got pretty much the same application as I had before. Data grid, progress bar, click me button. Okay. And down here, I'll talk about in just a minute. I have a little extra control. But here we go, and we'll just go ahead and start parsing. And as you can see, data's parsing, progress bar is updating, label's updating. It's moving at a pretty decent speed, already at 10%. And the most important part, the click me button works again. Another nice feature of Charlie's class is that you can actually adjust on the fly how much time you leave for everybody else at epsilon. So right now, epsilon is at 1%. And so as you can see, I'm parsing data pretty fast, but I'm only leaving about 1% of the frame time for everybody else. I can actually increase epsilon, and I can even increase it all the way to 99%. As you can see, the parsing immediately slows down because we're giving the green thread less time to execute during a frame. And the click me button still, but the click me button still works. And if I had a lot more going, you know, it'd be able to do a lot more. Okay. So, okay. All right. Let's go back to, okay. Okay, so let's take a look at what we've done so far. Okay, we have some block of code, some algorithm that can be broken up into little steps. So at first, you know, we tried to solve this problem of too much work in a frame by breaking it up and then scheduling, you know, sections of it to execute at different times. So one solution we looked at was using enter frame, and there I just explicitly scheduled one, you know, bit of work to be done at the beginning of the frame when that enter frame event is handled. I also tried using a timer so that every time the timer ticks, I do one block of work. And we found that, okay, they worked out pretty well. Our application remained responsive, but the problem was that we were doing too little work. We were spreading it out too far, and our runtime got atrocious. So we fixed that by saying, all right, let's do a little bit more work every time I do it. So we went down here and we said, all right, so every time I handle enter frame or every time the timer ticks, I'm going to do multiple batches of work. And that worked out pretty well too. We were able to make our parsing example a little more efficient, but we also ran into issues where we had to kind of trial and error, try to find that optimal amount of work to do so that our runtime remained good, but that our application remained responsive. And we found that, okay, well, that's not the greatest solution. You might have to keep fine-tuning it. You have to waste time actually, going through this process of trial and error. So how can we make the solution even better? Well, we said, all right, well, let's look at it from a different angle. Instead of trying to find the optimal amount of work to do and schedule it, we're just going to say, all right, whatever I'm doing is important, so I want to do as much of it as possible. I'm going to leave some epsilon, some sliver of frame time for everybody else. And if I run into into the situation where I only have epsilon left, I'll just stop parsing, I'll start parsing. I'll stop running my algorithm for now, and then just let everybody else, that needs to run in the frame use epsilon. And then next frame, I'll come back and run my green thread again. Okay, so comparing our solutions with a little more in terms of hard numbers. So our original solution, just that for loop, looping through the lines of data, parsing it out, doing all that stuff. So if it hadn't have crashed, if it hadn't have timed out, it would have taken about 58 seconds to parse the data. Okay, so the slowdown on that is none, right? That's our original algorithm. It just basically grinds through all data, finishes it up, no slowdown whatsoever. Was it responsive? No. And in fact, it crashed, and that's not what we want. So we said, all right, well, let's try something different. So one of the solutions we looked at was using a timer. So on one end of the spectrum, we just did one loop of our algorithm, per frame. That's kind of how we set it up. And we found that our runtime was somewhere along the lines of 11 hours. Very large slowdown. But was it responsive? Yes. So we got responsiveness, but our runtime was absolutely terrible. So we said, all right, well, let's go the other way. Let's do a lot of work per frame. So if we set it about 20,000 iterations of the loop every time we have every time this timer ticks, our runtime's about 62 seconds. Okay, so the slowdown in runtime is kind of small. 4 seconds, not bad. Was it responsive? Yeah, but not really. You can kind of see when we get up to that amount of work, things were getting sticky, things were getting slow. It wasn't even rendering the effects. So the thing with using those kind of solutions where you're trying to find this good this optimal amount of work you do, you have to balance it between this end of the spectrum with long runtime, big slowdown, but lots of responsiveness with pretty decent runtime, not too much slowdown, but not too much responsiveness either. And we had those nice solutions in the middle, 3,000, 4,000 iterations per timer tick where we balanced it out. We got decent runtime and decent responsiveness. Well, that's a lot of work figuring all that out. So we decided, okay, let's try a different approach, green threading. So if I'd actually run my green thread, example all the way through, and if I kept the share at about, I think, whatever the default was, I think it was like 1% for everybody else. Our runtime is about 85 seconds. All right, that's about, 27-second difference? Not great. Depending on, whatever the requirements of your application, this could be acceptable or not acceptable. But again, you can adjust that by adjusting the share. But the most important thing is that we were able to, balance out the amount of work we do with, and balance out runtime and responsiveness. And we didn't have to kind of keep fiddling with it. We let the green thread itself figure out, how much work can I do and, and still leave time for everybody else. So overall, green threading, the not so good. You still have overhead, more code complexity. Okay, instead of just adding some event listers, I had to subclass another class and arrange all the do all this extra work. And not only that, but I still had a runtime increase because we're still spreading out the work and also whatever increase we get from our overhead. And there are cases where you'll still need to make some adjustments to the time left over for the rest of the events. You might be doing a lot of really intensive things in one application, and you might still, find that you have to maybe give, other parts of the application more of the frame time. But the good. All right, so we achieved application responsiveness. We did that by saying, we always want to give everybody else, that the Flash player needs to take care of some time. So they're always going to have some time to at least, render the screen, update a few things, maybe even take in some user input. They always have that. And another good thing is that, we let the green thread itself determine how much work to do, okay? There's none of that figuring out, okay, how many loops I have to do. The green thread just timed itself and said, okay, I've done too much work. You guys can have at it. And I guess from an architecture kind of, how your code is structured kind of way of thinking, it's really nice to have this green thread, this class that encapsulates all this functionality for us. All that management of time, all that, management of those bookkeeping variables, we can just wrap it up in a class and just say, okay, here's your work, go ahead, take care of it. And we don't have to meddle too much. And anybody using our class can just be like, all right, well, I just start it up and let it go. And if I need to, just to share a little bit. But it's nice to have all that functionality encapsulated and, makes things just a little bit neater for you. Okay, so the question I got at one session was, can you do multi-threading with this? And you certainly can. Just kind of extending the concept of maintaining this epsilon for the rest of everybody else to execute. So you can think of it, you can think of multi-threading as, all right, I've got a bunch of green threads. I'm going to queue up these green threads as my user instantiates them. And I still have that same amount of time allocated for green threading, this frame rate minus epsilon. And I'm just going to divide that time up among all my active green threads. So, and when a green thread finishes executing, they get booted off the queue, everybody gets more time, cool. And this is already implemented in Charlie's library. All that management is taken care of already. Just create as many green threads as you want, and the library will take care of it for you. Okay, I'm going to take a quick break, and I want to give a little bit of props to people who need props. This topic was kind of introduced to me by Doug Knudsen, a great developer at Universal Mind. He and I worked on a project together where we actually did do text parsing, CSV text parsing, and we found we had a lot of application slowdown and freezing because of the amount of work we were doing. So, and that's how kind of I got introduced to it, and Doug got introduced to it through Charlie Hubbard. And Charlie wrote a set of really great blog posts exploring this general idea of concurrency and ActionScript. And most of the materials that I talked about today are in these blog posts. If you find it interesting, I highly encourage you to go and read Charlie's stuff. If you find that you actually use it, let Charlie know. He said he's really looking for use cases for this. He really wants to know how people are actually using these techniques. Charlie's class, he kind of built off of some work done by Drew Cummins, and he wrote a blog post about it, and he has some really cool examples of it. I think he did some pathfinding examples and some image processing examples, so if that interests you, take a look at that. And a little bit of what I talked about today also came from a post that Jesse Warden did. And he talked about parsing and rendering lots of data in Flash Player, and he even touched on Pixel Bender a little bit and about why he decided not to use it. But again, great article, take a look at it. Okay, so I'm going to wrap things up. So what we're talking about today is situations where we have applications that have long-running code, and this long-running code can hang because basically the Flash Player event queue gets stalled. It can't take care of everything that it needs to take care of. So to keep the application responsive, we just took this long-running block of code, broke it up into small jobs, and made sure that we triggered these jobs at different times. And we gave the event queue a chance to process their events to catch up. Okay, so we explored a few different ways of doing this, but the one that I personally like and that I'm advocating here today is green threading. And the idea behind green threading is not just scheduling work at different times, but rather to go at it from the approach of I want to fit as much work on this job as possible in a frame, but I still want to leave time for other events. So I think it's a much better, especially when you're talking about pieces of your application that are critical, that are important, that need to get done. It's probably I personally think this is a great way of kind of looking at it, and a great perspective, and a great technique. But unfortunately, yeah, there are a couple of costs that you have to be aware of. Number one, you're going to have more complex code, having to subclass and set these things up. And it's not just a straightforward grinding of the work, but and also because of this overhead and because of the sheer fact that you're scheduling things out, you are going to have a little longer runtime. And again, just overall, if you find yourself in a situation where, you have this problem, obviously, as developers, we have to kind of decide what's appropriate. But if you run into the situation, I highly, advise, or suggest that you take a look at green threading. And, if it works for you, awesome. Okay, I'm done. So I want to thank you guys for, well, you guys all had to come here because, it's a schedule. But thank you guys for coming to Capital Flash Camp. Feel free to ping me comments, questions, tell me I'm talking way too fast. Email, Twitter, website, that's what that is. And I included links on the slides for all these blog posts, and I would advise you to take a look at it. If you're really interested in that frame execution stuff, all that, the nuts and bolts of the Flash player, there are a couple really great articles on that. And is there any questions? Right to left.
So I just want to make sure, it looks like the green threading works on the nominal time for the frame as opposed to the actual. If you leave 10% of the frame left over for processing, but the frame actually can't do it in that amount of time, it will still stretch the frame.
Yeah,
It's not, the green threading, at least the technique here, doesn't look at how long the last frame actually took as opposed to
right. Yeah. It's kind of, it's making assumptions that this is the amount of time, right. Yeah, it's all kind of ideal of like, ideally this is how long it takes, so I'm going to try to go along that guideline, yeah.
Is it possible to extend, for example, most of the time if you weren't doing anything, you could use, it would be happening in the right, but when you click the button, the rendering time would stretch the frames. Is there a way to even sense how long a frame is taking and then scale it that way?
I mean, certainly what you could do, and it's kind of come up a bit when I've talked about this, kind of just, like taking it a step farther and saying, okay, well, let's measure, and then adjust for that. And I think it's a great, way to extend the class. And it's certainly something you could do. And you can do that. I mean, just really quickly, the way that this works is really simple. There's a function called getTimer. And it basically just returns the number of milliseconds since the start of the frame. So, I mean, that information you could definitely use and just keep a track of that. And I think that's a great idea. And it's definitely something that, if you really want to optimize and really want to kind of get down into using this, it's definitely something you should consider. Okay, yeah.
I apologize if this was answered in the first few minutes
Okay.
this morning, but are these slides going to be posted on the Capital Flash Camp site? Or?
Yes?
Sure.
Yes, sure. I'll also post them up on my website, but I guess you guys would have to. Yeah, sure. Okay, sir?
This seems quite suboptimal because it makes the developer decide how much to reserve time per frame or per time slice. Instead, wouldn't it be better to, when you break out of your loop, just add that to the queue? Then you'll process whatever you have in that queue, and it'll come back to it. If there's nothing in that queue, it'll come back to it really fast. You don't have your delay time, and it does it automatically, and it optimizes.
I'm sorry. So I'm sorry.
Every time through your number of iterations, you throw it on the queue, not scheduled for the next frame. You don't reserve time for it per frame. You use the queue to process all the things that are waiting. If the user, in using this, is doing a lot of stuff, there's a lot of stuff on the queue, and you may need more than that time you've incremented. If the user is just sitting there doing nothing, you use very little time, and it comes back from the queue right away.
Well, there's a couple things. I mean, that's a good point. Number one is that you can actually do that. Like you can use like say call later, and it basically just gets thrown. You can kind of set it up that way. Again, you kind of run into problems where at the same time where you're throwing something back on the queue, you still have to kind of figure out like there is going to be still some slowdown because you're kind of breaking things up over time. You can't. I'm drawing a little bit of a blank here, but while you can dispatch something to get processed in the queue, but there's a lot more going on in the application. I'm so sorry. Bringing the thought back in my head. It's kind of hard to explicitly put something on the queue and expect it to be run, immediately because there's so much like events and everything kind of being dispatched. And you still kind of, I feel like you still would run into the situation where, you know, well, at the same time, you want to take advantage of every time that you do work, because, you know, as developers, we have some control over what gets thrown in the queue just simply by what we put into the application, but we don't get to actually manage the queue itself. You know, it's all internal to Flash Player. So in a sense, it's, you know, you're right, it's not the, you know, it's not the most ideal solution, but at the same time, you know, there's so much that we do not get a handle on that, you know, we kind of have to work within, you know, the bounds of what we have control over, and which is why, you know, sometimes that we get into these situations where, yeah, a lot of it is up to us to figure out ways to work around the system. So, but it's an interesting idea. I mean, I'm trying to think of, you know, a way that you could really like make sure that something ends up on the queue rather than having to worry about, well, you know, based on frames, which is, you know, just absolutely correct, which is the way it should be done. You want to just make sure that it just gets back on the queue, you know, after everything else needs to be done. But I'm at a loss a little bit about trying to figure out how to do that on this platform. Yeah.
Can you change the frame rate for the Flash Player?
Yeah, you can.
Can you change it dynamically while you're running it?
That's a good question. I'm not sure. Does anybody know if that's is that compile time or runtime switchable?
I know on template 1 it's supposed to take it down to 1 for stuff that's not physically screened.
Must be able to do it runtime.
If you could do it dynamically, kind of tweak it a little bit, then that's probably another thing that you can add to the process to
Mhm.
improve it, right?
Yeah, exactly. Just drive it.
Maybe like it's a little bit short of completing something, you can extend it or increase it.
I want to say that there's probably a property that you can set on the application object, but I could be totally wrong. Yeah, you can set it on the application. Yeah, so you can. Any questions?
Before running the next run function,
Mm-hmm.
does it kind of get the average of previous runs so that decides
Mhm.
whether to run,
Mhm.
make the run or not?
Straight up, like the code that I'm using today in Charlie's library, it's pretty just rudimentary. It just kind of, you know, is only concerned with the run that you're in. But, you know, as was brought up, you certainly could do that. You certainly could maybe somehow, in a very concise way, keep, you know, records of how your last runs did and then adjust it that way. You totally do that because all you need is just to figure out, you know, how much time have I used up. So you can certainly do that, but it's not in this library as of yet. Cool.
Thank you very much.
Thanks.